Good day, I am Parish Jado Ocampo and this is my project in Digital Integrated Circuits ECE222-D01. So I was tasked to design a schematic of a 2-input multiplexer for static CMOS and dual rail domino using electric 6.03. The contents of my presentation includes the introduction, advantages and disadvantages, sizing, and schematic simulation results. So let us now first proceed with the logic style. So what is a logic style? Logic style is the way how a logic function is constructed from the transistors. It influences the speed, area occupied, power dissipation, and wiring complexity of a circuit. And all these characteristics may vary considerably from one logic style to another style and thus make the proper choice of logic style crucial for circuit performance. And we have here three types of logic style. The first one is the complementary CMOS logic style. Any logic function in complementary CMOS is understood by NMOS pull-down and PMOS pull-up networks connected between the gate, output, and power lines. And all the input signals are connected to the transistor gates only. When we say complementary CMOS, when the NMOS pull-down is high, the PMOS pull-out is low. And when the NMOS pull-down is low, the PMOS pull-up is high. And the static CMOS falls under this category. Next, the dynamic logic style. The operation of dynamic logic is based on storage of charge on capacitive node. And these are the fastest, have zero static power dissipation, and are sensitive to noise. And the domino and dual rail domino falls under this category. Last but not the least is the pass transistor logic style. It reduces the number of transistors required by allowing the primary inputs to drive gate terminals as well as the source drain terminals. And these are the examples of 2-to-1 multiplexer using the different types of pass transistor logic. So we have here the complementary pass transistor logic, the energy economized pass transistor logic, the DC VSPG, LIP, CMOS transmission gate, 2-pass transistor logic, and PPL, and so on. So let us now focus with our first topic, the static CMOS. So this is the block diagram of a static CMOS. It has a pull-up network which comprises of PMOS only and a pull-down network which comprises of NMOS only. So static CMOS is a combination of two networks, pull-up network and pull-down network. The advantages are, first, it's simple in design. Second, it is insensitive to variation. It has good noise margins and fast operating speed, and it has low power. The disadvantage, nevertheless, is the performance or area constraints occasionally dictate the need for other circuit families, and the most important alternative is the dynamic circuit. For sizing, the NMOS has 0.8 micro in width and the PMOS has 1.6 micro in width. This is the constructed circuit of 2-to-1 multiplexer for static CMOS, and the sizing is necessary to equalize the response time of charging and discharging of a load capacitor in the pull-up network and the pull-down network. I want the sizing ratio of my circuit to be 2:1, and the rule for sizing is when they are in series, we must multiply the size by the number of the components in series, and then when they are in parallel, retain. So this is my pull-up networks and this is my pull-down network. So let us first proceed with our pull-down network. From our pull-down network, as you can see, we have here a 2 transistor in series which has a 0.8 micro width. So 0.8 micro times 2 is 1.6. Another 1.6 on the right side, and since they are in parallel, so the value will, I think it's 1.6. Next is I have here two transistors in parallel, and it has a value of 1.6 micron feet, so the value must be retained, same with here, but the two parallels are in series, therefore 1.6 times 2 is 3.2, and the ratio will be 3.2 is to 1.6, or 2 is to 1. Again, this is the block diagram of a static CMOS, and the symbol for, since we are asked to design a 2-to-1 multiplexer for static CMOS, let us now first proceed with our multiplexer. So this is the symbol for 2-to-1 MUX. It has a two inputs, I sub 0 and I sub 1. It has a selector input and then an output Y. The truth table, so this is the truth table. We have a S here, and or the selector or the switch, and then we have here BY. If the selector or the switch is low, the output will be all the data inputs from I sub 0. And if our selector or switch is high, the output will be all the data input from I sub 1. And from the truth table, we can create the Boolean expression of S bar I sub 0 plus S I sub 1. And to construct a CMOS circuits, we must take note that when ANDing, all the PMOS must be in parallel and MOS must be in series. And when ORing, all the PMOS must be in series and NMOS must be in parallel. And this is my schematic for the circuit. Let us now first proceed with our Boolean expression. So for Boolean expression, we have here S bar ANDed with I sub 0 and ORed with S ANDed with I sub 1. This is our pull-up network, which must comprise of PMOS only. So for PMOS, when they are ANDed, they must be in parallel. So S bar must be in parallel with I sub 0. S bar I sub 0. Then ORed, they must be in series with another parallel S I sub 1. And then for our pull down network NMOS, when ANDed, they must be in series. So S bar in series with I sub 0 in parallel with another series of S I sub 1. So this is the design of 2-to-1 multiplexer using static CMOS simulated in electric 6.03. I have here an input voltage of 3.3. The selector switch, which has 20 milli and 40 milli T rise and T fall, and then I sub 0, which has a 5 milli and 10 milli. I sub 1, 10 milli and 20 milli, and then we have here the output Y. Again, this is my the constructed circuit. Let us check first if the connections are correct. So this transistor must be connected in S bar, or the inverted selector switch, and this is for I sub 0. This is for selector S. This must be connected to our I1. Then this must be connected to our, again, S bar, I sub 0, S, and then I. So the connections are correct. Let us now see the video for simulation. So first, open the electric application, open the library static-cmos.elib, and then to simulate, we must extract the netlist, and to do that, we must click the Tools, Simulation Interface, write Spice Deck, and then save as the all files, and then .cir. Since we know that our circuit is working, we must open the WinSpice file, open our files, and since our circuit is working, the WinSpice is also running. So as you can see here, all the outputs or the waveform of our input 1, output, input 0, and the selectors are stacked in a single plot. And to be able to see all the waveform, we must increase the position of our waveforms. And since our input voltage is 3.3, we can use 3.5. Add 3.5 in every waveform. But I used 4.0 just to be precise. So type plot, space, the V select. I want to see the V select first, and then plus 12, and then Vi sub 0 plus 8, and then Vi sub 1 plus 4, and then the output V of Y. So this is the output of my simulation. So this is the simulation result. This is, the red one is our selector, the green one is the I sub 0, the blue one is the I1, and the yellow is the output. From our truth table, if the switch is 0, the output will be all the data input from our I sub 0. So if the switch is 0, so this is the 0 of the switch, or the low, the output is all the data input from I sub 0. And if the switch is high, the output will be all the data input from I sub 1. So this is the output from I sub 1, output from I sub 0, output from I sub 1, and output from I sub 0. So next is the dual rail domino. This is the circuit for a dual rail domino. Dual, it has two outputs, two PMOS components, and the circuit and its complemented circuit, the foot transistor, and two inputs. So the dual rail domino is also known as a differential cascade voltage switch, or the DCVS. And a footless domino circuit design is a data-driven technique where pre-charge signal is substituted by the input signal. So the disadvantages are, first, domino only performs on non-inverting functions like AND, OR, but not NAND, NOR, or XOR. And the dual rail domino solves this problem by taking true and complementary inputs and producing true and complementary outputs. Second advantage is no static power dissipation. Third is better than ratioed logic. Fourth is careful in design, and a clock signal is needed to be able to function. So the disadvantages are, first, the existence of foot transistors slows the gate somewhat as it presents an extra series resistance. Thus, I did not use a foot transistor in my 2-to-1 multiplexer dual rail domino. So domino gates suffer from higher noise sensitivity than their static CMOS counterparts, and this is because of their low switching threshold voltage, which is equivalent to the VTH of the pull-down NMIS devices. For sizing, I use 10 micro for the width of PMOS and 100 micro for the width of NMOS. The sizes were chosen to make sure that the pull-up networks and pull-down network reach its rail level. So again, this is the circuit for dual rail domino. It has two operations, the pre-charge and evaluate, or the low and high. This is the truth table for the dual rail domino. This is the output signal H, and this is the output signal L, or the inverted output. If the signal H is 0 and the signal L is 0, they are in pre-charge mode. But if the signal H and signal L are in 1, those are in valid outputs. And as you can see, in signal H, if the output is 0, it means 0. But if the signal H is 1, it means 1. And take note that when the signal L is 1, the real meaning is 0. And when the signal L is 0, the real meaning is 1, because signal L is the inverted output of the signal H. Signal H and signal X. So, for the construction of the circuit, for ANDing, the NMOS must be in series and the NMOS must be in parallel when ORing. And again, from our Boolean expression, S bar I sub 0 plus S I sub 1. Excuse me. So, this is the constructed circuit and this is the complemented circuit. So, NMOS in series must be NMOS is in series when they are ANDed. So, S bar in series with I sub 0. Or means they must be in parallel with S I sub 1. So this is our first circuit. And the second circuit is the complement of this circuit. So if the S bar and I sub 0 are in series, they must be in parallel here. And if the same with the S and I sub 1, they must be in parallel. And if the S bar I sub 0 and S bar I sub 1 are in parallel here, they must be in series here. Same with the literals. If we use S bar here, the complement of S bar is S. Complement of I sub 0 is I sub 0 bar. The complement of S is S bar and the complement of I1 is I1 bar. So that's, you have to input here the circuit and the complemented circuit. This is a 2-to-1 multiplexer using dual rail domino simulated in electric 6.03. I have here 3.3 input voltage again, 80 milli and 160 milli time rise and time fall of the clock. The selector, which has 40 milli and 80 milli time rise and time fall. And then I have here I sub 0 and I sub 1, the inverted I sub 0 and inverted I sub 1. We also have here the output voltage 1, which is connected to our first circuit, and then the output voltage 2, which is connected to the complemented circuit. This is the video presentation for the simulation. Open again the electric, open the library, and then open the project. And again, to simulate, we must extract the netlist, and to be able to do that, we must we must press the tools, simulation, interface, and then write spice deck, and then all files, save as type into all files, and then save as .cir. And as you can see, there's no error in my circuit. And so the next thing that we need to do is to simulate it in WinSpice. So file, open the WinSpice file, and since our circuit has no error, the WinSpice is running. It will take a while. There. So again, the output waveforms are stuck in a single plot. So we need to increase their position by 4 to be able to see all the waveforms in our plot. So we have here the select, input 1, input 0, the clock, the output 1, and the output 2. So we have plot the V of clock plus 20, and then V of select plus 16, V of I sub 0 plus 12, V of I sub 1 plus 8, and then V of V out underscore 1 plus 4, and then V of V out underscore 2 plus, that's all. Press enter. There you are. So this is my simulation output. This is simulation result. So again, this is the clock 0101. This is the selector waveform. This is my V I sub 0. I sub 0. This is my I sub 1. This is my output 1, and this is my output 2. According to our operation, table of operation. So if the signal is 0, the signal H, or the voltage output 1 and voltage output 2 are 0, so they are in pre-charge mode. But my circuit is a footless domino circuit, and a footless domino circuit is a data-driven technique where the pre-charge is substituted by the input signal. So instead that the pre-charge is 0 and our evaluate is 1, our pre-charge will be our input. And from our truth table, if the selector switch is low, all the data inputs from I sub 0 will be output to our Y. And if the selector switch is 1, all the data input from I sub 1 is output, our output. So this is our clock, this is our pre-charge, this is our evaluate. So all the outputs will be seen in our pre-charge mode. So this is pre-charge mode, this is the clock, and then we have your 0 and 1 in a single period of, and half period of the clock. So it's 0 means the output will be all the data input from I sub 0. So this is our I sub 0. And then when the switch is high, the output will be all the data input from I sub 1. And then evaluate. And then again I sub 0, I sub 1, and then evaluate. Output 2 is the inverted output of our inverted V out. So this is our inverted I sub 0, our inverted I sub 1, and then the evaluate will be retained. And that ends my presentation. Thank you and stay safe.